Here's our first example of Stokes' theorem. So our curve C is the positively oriented intersection of two different surfaces. We've got a vector field in 3D given to us, and we're going to use Stokes' theorem to evaluate the work done by our vector field around the curve C. All right, so the idea in going into this problem is that we don't want to compute this quantity directly. We want to use Stokes' theorem, which says this quantity is the same thing as the surface integral over S of the curl of F dotted with n ds. So we need to work towards computing this quantity here. First thing we could do, calculate the curl of F. And then after we've got that, we could calculate n ds, do our dot product, and then do our double integral from there. So before we get too far with this, I'm always tempted to draw a sketch. So let's try that. We're in 3D. If we look at our surfaces, one of them is a cylinder. So x squared plus y squared equal 1 is a circle of radius 1 in the xy plane, but in 3D, it's just a circular cylinder. And then that cylinder is being intersected with this plane, y plus z equal 4. Okay, so that would look something like that. We've got that sort of a plane happening. And when you let those two intersect, let's erase a bit of the detail here so that we can draw a clean intersection. What we'll get is an ellipse, looking something like that. So that C, it's positively oriented, so meaning counterclockwise from above. So now in the context of Stokes' theorem, when we say curve C, that's acting as a boundary curve to our surface. So if you want to visualize your surface S in this picture, that would be any surface that has C as its boundary. So it could, for example, be that ellipse type shape that we see here, but it could also be something like a paraboloid type surface. As long as it's got C as its boundary, we're going to come up with the same value for this double integral here. So there are lots of options for how you could set up your surface as long as it's got that boundary curve. I'm inclined usually to take the simplest possible version of the surface. So let's get into our calculation by calculating the curl of F. We're going to set up a 3×3 determinant, ijk, partial derivative operators, and then we'll fill in the components of our vector field, which we're told in the question, minus y, xy, and z squared. Okay, so let's get this calculated. We'll expand along the top row here. So vector I times this little 2×2 determinant. Well, delta by delta y of z squared is 0. Delta by delta z of xy is also 0. So the I component is just 0 there. Minus j times, now we'll cross out the row and column containing the j, and again we're getting 0 for that 2×2 determinant. Then finally we have plus our vector k. I think something interesting is going to happen here, so we'll look at this little 2×2 determinant. Delta by delta x of xy is going to be y. And then we're going minus delta by delta y of negative y. So that's minus -1, in other words, plus 1. All right, so that gives us our curl of F. If I just write that in component notation, 0, 0, y plus 1. Great, so that's the first piece of the puzzle in terms of getting this right-hand side here calculated. Next thing we need to do is calculate n ds. So let's think about our surface. Let's look back at the question and see what we know about our surface. So in fact, we were given some information about this curve C. And we know that the curve is coming from the intersection of the cylinder with this plane. So this is where we need to look at our pictures that we drew over on the side here. And we need to get specific at this point about what our surface is. So I would say, let's keep it simple. Let's say that our surface is that ellipse that's being enclosed by our curve C. So just highlighting this picture here. And so if we think about on which surface our surface S is lying, well, it's really coming from this plane y plus z equal 4. So we'll write down that equation there. And we could actually solve that for z relatively easily. So you could say our surface S is z equal 4 minus y, but it's not the entire plane. It's being cut off by the cylinder. So the way we're going to interpret this is we'll say this is our surface S. But when we get into our double integral, we'll actually think about restricting that to a certain region of the xy plane. So this circle, in fact, unit circle that we're seeing in the xy plane, that's going to be our region of integration, but the surface itself has equation z equal 4 minus y. Okay, so that's good news, because when you've got a surface where z is given explicitly in terms of x and y, there's a fast way of computing vector n times ds. So we're just going to go either plus or minus negative z sub x, negative z sub y, 1 times dy dx to get our nds. All right, so let's try that. We'll go plus or minus. We're looking at this equation here, z equal 4 minus y. So let's take our partial derivatives. Z sub x would be 0, z sub y would be negative 1. We're changing the sign on that to get 1. And then we've got 1 dy dx. Okay, and then we use the sign convention to decide whether we're going plus or minus. So I'm going to redraw our picture here. Our surface, simplest possible surface that could have that boundary curve C, was just this ellipse here. And since that's not a closed surface, we're going to choose the unit normal vector that goes upwards. So if I draw a picture of n, would look like that. That's our upper unit normal vector. And so we are going to choose the plus. So the whole reasoning here is we want to go upwards. So that implies that our z component should be positive. So that implies that we should choose the plus sign. All right, so we got our nds done. Let's just write a cleaned up version of that. So it is 0, 1, 1 dy dx. And now we can actually think about taking the dot product of the curl of f with nds. And that way we're going to have the quantity that we need to do the double integral of. Okay, so we said curl of f was 0, 0, y plus 1. And we're now dotting that with this 0, 1, 1 times dy dx. So that's going to work out pretty nicely. That's just going to give us y plus 1 times dy dx. Great. So now all that remains is to do the double integral over our surface of this quantity. Okay, so let's flash back to the question for a second just to make sure we're in the right context here. So the problem is use Stokes' theorem to evaluate this specific line integral. Okay, so if we really wanted to answer the question clearly, this is where I would say, well, the line integral that we want to evaluate by Stokes' theorem is equal to this double integral over our surface. And then we'll go ahead and compute this double integral. And that way we've just got the logic right in terms of answering the question clearly. All right, so we're going to do a double integral of, we already figured out our integrand up here, y plus 1 times dy dx. And now that we've written this in terms of x and y, we can write the subscript on the double integral here as r. So again, let's draw our picture and understand all the geometry that's happening here. So we've got this cylinder, and we've got this curve C, which is an ellipse formed by intersecting that cylinder with a plane. So there's C. We decided to take the simplest possible surface that would have that curve as its boundary. So we're just taking the full ellipse as our surface. Okay, and then if we project this on the xy plane, then what we'd be producing is just that unit circle. So R is that projection on the xy plane. All right, and that's just coming from the equation of the cylinder. So x squared plus y squared equal 1. And I would say this is going to be much nicer if we move into polar. So r squared equal 1, which means r is equal to either plus or minus 1. But because we're talking about a radius, we're going to use r equal 1. And that tells us that our region r in the xy plane is just a disk of radius 1. So r is going to go from 0 to 1, and theta is going to go from 0 to 2 pi. Okay, so let's think about moving this entire integral here over into polar, and then we'll be able to finish our computation. So our integrand, y plus 1, would be better expressed as r sine theta plus 1. Remember that in polar, y is equal to r sine theta. And then the dA here becomes r dr d theta, and we can put our limits of integration on there. So 0 to 1 and 0 to 2 pi. All right, now in order to proceed with the integration, let's actually expand out our integrand. It's actually r squared sine theta plus r that we'd like to integrate. So we'll keep our outside integral and outside differential on here. Integrating with respect to r cubed over 3 times sine theta plus r squared over 2, and we're going to evaluate that at r equal 1 and r equals 0. So that's going to look like the integral from 0 to 2 pi sine theta over 3 plus 1/2, and then we can do our integration with respect to theta. So minus cos theta over 3 plus theta over 2, and we'll evaluate at 2 pi and then at 0. All right, so let's try plugging everything in. At 2 pi, we're going to have minus 1/3 plus pi, and then we'll subtract off the value at 0, which is going to be minus 1/3. So we can see that the 1/3 terms cancel out, and we're just left with pi for the final value of our integral. Really what we did in this problem was we used Stokes' theorem in the forward direction. Yeah, let me scroll to where we actually wrote down the equation for Stokes' theorem. So if you take this thing and you say, actually, I want to rephrase it as this thing here, and then do the calculation that way, that's what I would consider the forward direction. So we avoided the line integral by instead doing the calculation with the surface integral. In this example, we're going to use Stokes' theorem to evaluate a certain surface integral where we're given a vector field in 3D, and we're given a description of the surface S that we're interested in. So I think first thing I'll do is just draw a picture. Always good to make this a bit more visual. So our surface S is part of the paraboloid, z equal x squared plus y squared, that lies below the horizontal plane, z equal 4. All right, so this paraboloid is just being cut off here to make a finite surface. So S, just the side of that paraboloid. And let's write down Stokes' theorem just so we're clear on what we're supposed to be doing here. So the statement of Stokes' theorem says that the line integral around a closed curve of f dot t ds is equal to surface integral over S of curl of f dot n ds. So what this question is asking us to do is to use Stokes' theorem backwards. They're saying we want to figure out this thing, but we want to use Stokes' theorem to do it. So we're going to rephrase this thing as this thing here. So this is the work done by F around C. And we've talked in previous videos about work. So when you see this expression here, the way that you actually think about calculating it is you say, well, it's going to be line integral around a closed curve of our calculation formula for work is actually p dx plus q dy plus r dz. So I'll write this down in a more formal way when we actually get into the calculation, but that's just sort of a little preview of where we're going. So in order to solve the problem, what becomes important here then is this curve C. So let's make sure that we can highlight that on our picture. In the context of Stokes' theorem, the curve C is the boundary curve of our surface. So think of that as being just the edge of our surface. It would just be this circle that we see in our picture here. We take it to be positively oriented, meaning it's going counterclockwise when viewed from above. or you can think of that as it keeps the surface on its left as we travel around the curve. So we want to come up with a description for that curve C. That's really our first piece of work here. So let's think geometrically about where C comes from. Well, it comes from intersecting the paraboloid with the plane. So if we say z equals z, and here are our two surfaces given in the question, we're saying x squared plus y squared has to equal 4. And our goal is to parameterize this. Parameterize with just a single parameter because it's a curve. So if we went into polar, we could say r squared equal 4. That would mean r equal plus or minus 2, which in the language of polar means r equal 2. And then we could say, all right, so if we write down our values of x and y using polar coordinates, we could say x equals r cos theta, y equals r sine theta. And we are in 3D, so we need to parameterize all 3 variables in the language of some new parameter. Okay, so we'll talk about z in a second, but first let's deal with x and y. So we've decided that the radius of that circle that we see in our picture there is 2. So we can say x equals 2 cos theta, y equals 2 sine theta. And then let's think about what's going on with the z value for the curve. So this curve is formed by the intersection of the paraboloid with the horizontal plane, z equal 4. So everywhere on that curve, z is just going to be 4. Z is constant. All right, so that's a parameterization. I'll just copy down the z equal 4 here. If you like, you can rename your parameter t. Doesn't really matter what you call your parameter, but I would say slightly more conventional just to call it t. So I might make that switch here just because the notation will probably help jog our memory for line integrals if we use the kind of conventional notation. So I'll say this is the parameterization that we're going to choose. And we're also going to need the differentials of these things when we compute our line integrals. So we'll say dx equals minus 2 sine t, that's times dt. dy is going to be 2 cos t dt. And then dz will be 0 because z is constant. And anytime you parameterize a curve or a surface, you need to give the range of values for your parameter. So t is just representing our angle as we rotate around that circle, and we want to go all the way around the circle. So t is going to range from 0 to 2 pi. Okay, so that's a parameterization of our curve. And with that, I would say pretty much the hard work for the question is done. So let's get into the calculation. So again, let's refresh our memory on what we're trying to do here. We're supposed to use Stokes' theorem to evaluate this surface integral. Okay, so let's pretend that we didn't have that kind of recap discussion at the beginning of the problem. Let's say that we hadn't written any of this down. Here's how we would proceed. So we would say, here's what we're trying to calculate, the surface integral of the curl of f dot n ds. And we're going to use Stokes' theorem to say this is equal to the line integral around c of f dot t ds. And then we're going to say that's work. And the way that we actually calculate work is by saying line integral along our curve of p dx plus q dy plus r dz, where these p, q, and r are the components of our vector field. So this is where our vector field f is going to come into play. Let's scroll back to see that. Vector field f was minus 2y, 7z, and x. Okay, so let's plug those in here. So we got this line integral around the closed curve C. P is minus 2y, so we're going to go minus 2y dx plus 7z dy plus x dz. So just for reference here, I might write over on the side our vector field f, just so we don't have to do a ton of scrolling here. So it's minus 2y, 7z, and x there. So that's how we plugged into the pdx plus q dy plus r dz. So that all looks good. Putting everything in the language of t now, we're going to have minus 2y. Okay, I think I'll highlight the x, y, z values and the differential values up here. So minus 2y is going to look like minus 4 sine t, and that's going to get multiplied by dx, which is minus 2 sine t dt. Okay, and then we're going plus 7z, so that's 28, times dy, which is 2 cos t dt, and then happily the dz is 0, so our integral is not going to be too bad here. And then t value going from 0 to 2 pi. Great, so we're just going to clean this up and then we'll have our answer quite shortly. So integrating from 0 to 2 pi, doing our integration with respect to t. So I'm just going to factor out that dt because it's going to come up in both of these terms. And if we just think about expanding out here, we'd have 8 sine squared t plus 56 cos t with the dt factored at the back. Okay, so that's almost ready to go, but in terms of the integration, I would just use the identity here that sine squared t is going to be 1 minus cos 2t over 2, so that we can actually get that ready for integration. And what that means, if we multiply both sides by 8, then 8 sine squared t will become 4 times what we've got on the right side here. So let's take that 8 sine squared t and let's just think of that as 4 minus 4 cos 2t, and then we're ready for integration. So integrating 4t minus 2 sine 2t plus 56 sine t, and we're just going to evaluate that at 2 pi and then at 0. So plugging in here, we're going to have 8 pi. So that's an example of using Stokes' theorem backwards. Scroll up to our discussion that we had at the beginning of the problem. We avoided doing a surface integral by using the Stokes' theorem equation to rephrase that as a line integral. And that meant that we had to do the parametrization of our curve C in order to solve the problem. Congratulations on making it to the last video of this video series. If you made it through all these videos, then you have completed multivariable calculus. Thanks for watching.